All right. Well, then, first of all, thanks for the invitation, especially to Jacob, who invited me. It's my pleasure to be here and share some of my research with you. I'm a PhD candidate at the Pattern Recognition Lab at FAU in Germany. That's why it's dark here and probably not where you are. Yeah, so before I dive into the topic of my talk, which is about, my research project for my PhD, I'd like to, of course, thank my complete lab and also my cooperation partners in the geography department. Without all of those people, my research would not be where it is right now. Okay, so we all know that sea levels are rising, but the most important question now is by how much are they rising specifically? And to get there, we would have to know, so we have to have some glacier models because they store a lot of water. And the goal of today's talk is kind of to let you know one way to improve upon the current sea level rise estimates. And one way is to improve upon calving front positions, because calving front positions are one parameter for glacier models. But you might ask yourself now, okay, what is a calving front? So the calving front of a glacier is the edge where the glacier ends and faces the ocean, where icebergs break off, and this iceberg breaking off is called calving. Therefore, the name calving front. All right, so until recently, normally it was just, so the calving front position was detected manually in satellite images. But of course, this is quite time consuming, it's tedious, and it's also expensive because geographers who do that also want to be paid. So actually, it was not, so the calving front position was not located that often. So either glacier models rely on few and outdated detections, or the frontal ablation, which is the mass of ice that is lost at the calving front, is not considered at all in glacier models. And if this frontal ablation is neglected in glacier models, the sea level is actually overestimated. So the rise is overestimated by 2% per temperature change scenario from the IPCC reports from 2015 to 2100. So of course, we are here and want to do some machine learning. So we want to automate the locating of the calving fronts from the satellite imagery. And for that, I'd first like to introduce you to the data set that we devised. So in our data set, we have, let me quickly, how do we do that? Pointer options, awesome. So we have 7 glaciers, and images are captured from 6 different satellite missions. And we have images ranging from 1996 to 2021. And you might know, if you know about satellite imagery, that there are different modalities, like how you can get the images. So the normal one you will probably all know are optical images, for example, like in Google Earth. But there's also a different option, which is radar imagery, specifically called Synthetic Aperture Radar. And instead of using the sunlight, these satellites send out their own signal and just measure how much is coming back. So when you compare those two satellite imageries, you have an advantage from optical imagery because it's high in spatial accuracy and often also higher in resolution. But on the other hand, radar imagery is, as I explained, it's light independent, so it does not rely on the sunlight, which is good for glacier monitoring because most glaciers are close to the poles, and there you have at times very long nights called polar nights. So if from the optical images, you have a lack of data in that time period, but for radar imagery, you can get images also during the night. Also, radar can penetrate cloud cover, so you also get images during bad weather conditions. So for radar imagery, you get a temporal continuity in your data. So you cannot only see how the glacier is melting over the years, but also the dynamics within the season. So you can see how it moves. So it grows in the winter, and in the summer it retreats. So we decided to stick completely to radar imagery due to these advantages. The glaciers that we look at are located in Greenland. So here we have one, the Jakobshavn Isbrae Glacier. And then we have images from Antarctica. Here we actually have 5 different glaciers, the Sjøgen Inlet, the Dinsmore Bombardier Edgeworth, and then we have the Jorum Glacier, and close by the Crane Glacier, and lastly the Mappa Glacier. And then last of all, we also have images of a glacier in Alaska, which is called the Columbia Glacier. In the dataset, we have the SAR imagery and one label that directly shows the calving front versus the background. So here, this part is the ocean, and here we have the glacier. And then we also have a second label, which shows us the different landscape zones. So as I said, here, the ocean, then we have glacier ice in light gray, and in dark gray, we have rocks, and in black, these are kind of holes in the image. So it's an area where we have no information available. For example, from SAR shadow. Together with this dataset that we created, we also came up with a metric. And this metric, for every pixel in the predicted calving front, it looks for the closest pixel in the ground truth and calculates the Euclidean distance. It does that for every pixel in the prediction. And then to make the metric symmetric, we also look at the pixels in the ground truth and search for the closest pixel in the prediction and do that for all pixels. So we have for every pixel in the prediction and for every pixel in the ground truth, we have a distance, and over those we just build the average. So I showed you our data set, and of course you're all interested in the models. So let's dive into what we designed here. When we first published this benchmark data set, we also came up with baselines. Actually, there were 2, so one for each label. And both models have the same architecture, which is a simple unit with atriospatial pyramid pooling in the bottleneck. This part actually helps to deal with different calving front scales. So because there are big glaciers, there are small glaciers. And also it can deal with different resolutions from the different satellite missions. For the model that was trained on the zones labels, we could simply use the cross entropy loss. But for the model that was trained on the calving front labels, we devised a specialized loss. So we used the dice loss, but instead of simply plugging in the ground truth and our prediction, we multiply the prediction with some weights, which are calculated based on the ground truth. So everything that is right on the ground truth calving front is weighted really high, and in a surrounding area of the calving front, we then calculate a distance map. And the further away the pixel is from the front, the lower it is weighted. And outside of that boundary around the calving front, we just weighted with a constant weight. Yeah. And with that, we already get some metrics here, so some results. We have here the mean distance error and also a second metric, which just counts the number of images where no front is predicted. So sometimes it happens that for one input image, there's no single predicted calving front pixel, and then we cannot calculate a distance error. So what we simply do is count those, count the images where that happens. And of course, we want that to be low, that number. And what you can already tell is that the model, which was trained on the zone labels, works better than for the front labels. So it has a lower mean distance error, which is here in meters. So it's 753 meters that on average, that the predicted calving front is away from the ground truth calving front. And here you can see one result. In blue, we have the ground truth. In yellow, we have the predicted calving front, and pink just signifies the overlap of ground truth and prediction. And one thing that we noticed is that our prediction is quite ragged, which we did not like. So we had the idea to just incorporate a conditional random field, like in DeepLab version 2. So we incorporated in the post-processing instead of using a simple argmax to get from the neural network outputs the real predicted classes. So normally you just use an argmax, but instead we put in here a conditional random field, which gets the outputs of the neural network and additionally the SAR image. The conditional random field is also, so it has some parameters which are trained and optimized on our training data set. And here we can see the difference. So on the top, we have our original prediction. And on the bottom, we have the prediction using the conditional random field. So we see that some outliers are removed. Some disjoint fronts are connected. Overall, the prediction is smoothed. And more outliers are also removed. So actually that was more than we were aiming for, and we were quite happy with the results. But those are here qualitative results that I show you, but we also, of course, evaluated it in a quantitative measure, so with our mean distance error. And actually, we could decrease the mean distance error a little bit. But the more important part is that the quality of the prediction got better, which is not that nicely shown in the mean distance error. So that was one direction in which we were going, but parallelly, we had another idea. So for that, you have to know that at our lab, we mostly deal with medical images. And we noticed that in medical images, there is the same sort of noise, which is called speckle noise. And you have to know for biomedical image segmentation, there is one framework that is really good in most challenges for biomedical image segmentation. And that is called the no-new unit, in short, NN unit. And that actually just uses a unit, but optimizes the hyperparameters itself. So some hyperparameters are just set based on experience. So without the interaction of the user, but just by the pipeline itself, it always uses those hyperparameters. Then there are also hyperparameters which they set based on a fingerprint from the data. And also it empirically chooses some hyperparameters. But actually, we didn't really care about how it works. We just wanted to test it out for our remote sensing imagery. So we did two experiments. One where we just trained it on the front labels, and one where we trained it on the zones labels. But we also thought, okay, we have a high class imbalance here in the front labels. So why not use multitask learning? So we actually did 2 more experiments where we altered the NN unit, so the unit architecture in the NN unit. One where we used an early branching multitask learning unit, and one where we used a late branching unit. And as we had to implement some stuff so we had to touch the code, which we actually did not like that much in our experiments. So we thought there must also be a way to do multitask learning without changing the architecture here. And yeah, we came up with a fused label approach where we just dilate the calving front label and just copy paste it into the zone label. So we lose some of the ocean pixels and some of the glacier pixels, and instead have a calving front class, so a 5th class. And actually, all 3 multitask learning experiments worked significantly better than the single task versions. But within these 3, there was no significant difference. But as we did not have to touch the architecture in the fused label approach, and as it also takes up less memory, we claim that this version here is the best working model, so the fused label approach. And here you can see one result. So there are still a few false positives and false negatives here. But in general, we could improve the mean distance error by nearly 200 meters. And lastly, we also noticed that we have quite large images, so we always had to do patch extraction, as the images. So the median of the height and weight are roughly 2000 by 2000 pixels. So it's just too large to process as one. So we use patch extraction. But just like you can imagine, if you have binoculars and you look at some object which is far away, you just see a small part of it. And sometimes you cannot tell what it is. But if you look over the rim of the binocular, you can locate it, and due to the information around it, you can tell what it is. So we also thought that here with this patch, I myself would not be able to tell where is what. So because we lose this global information around it. So we stumbled upon a model that is called HookNet. The HookNet takes input 2 patches, one just a regular patch, and the other one actually cuts. So it shows the surrounding as well as the other patch. But it is downsampled to match the size of the target patch. So for this one, we actually want the segmentation and the context patch, as you call it, just shows the surrounding. It has a lower resolution, but a bigger field of view. And the other one has a higher resolution, but a smaller field of view. The HookNet comprises of 2 units, which are connected in the decoder. So the context branch, which gets the context patch, gives some information over to the decoder of the target branch. And we could improve upon this HookNet by using multiple hooks, so multiple connections from one decoder to the other. And also we incorporated a tension mechanism in this hooking mechanism. So when we feed the information over to the target branch. And lastly, we also use deep supervision here. So we call it Attention Multi-Hooking Deep Supervision HookNet, in short, AMD HookNet. And we could again improve upon our mean distance error by this time about 100 meters. And this is currently the best working model that we have. And here you can see a qualitative result. So it has still some false positive, but in general, the calving fronts are already quite nicely segmented here. To give you a short outlook on what we're working at the moment and hopefully publish soon, we are doing a model intercomparison study. So to see, because this is just our research, but other groups have also been working at similar challenges, and we just want to compare all that are already published. And we are also at the moment, we already have submitted this one. So it's a fully transformer-based approach. And of course, this rocks, and it beats the AMD HookNet again. If you're interested in any of my references, I'm happy to share them also in the chat. And with that, I'm open for any questions. I'm happy to have some small discussion as well.
Yep, it does look like we have a few questions in the Q&A widget. Cool. You want to hop over there?
Yeah, let me quickly see how I can do that. Boop, boop, boop. Zoom, I lost it. No, okay, I have to stop sharing to see it. Okay. All right, so we have the question, how many bands do the radar images have? Like how many channels and what wavelengths? So it has just one channel. If we have multiple polarization for one image, we actually combine them. What wavelength is a great question, and you can actually look that up yourself if you just Google the different satellite missions that we had. So that would be Sentinel-1. Let me check which else. It's definitely Pulsar, and here it is, ERS and AirSat, NVSat, and so on. So there you will get the wavelengths. Yeah, I think what radar frequency are you using? That's the same. You will have to look that up for the satellite missions. Okay, next question. Are the radar images available directly? I mean, is there any need to process the signals to get the images? So we published this benchmark data set, if you're referring to that. You can download it directly. You don't have to pre-process it. And yeah, if you're wondering about in general, yeah, you have to do some pre-processing, which includes, it's called multi-looking, and also some geocoding and so on. So there are some pre-processing steps involved, which have been already done by the geographers, so from my collaboration partners for our benchmark data set. Okay, what were some of the pre-processing techniques that helped in optimization? I'm not sure whether I get that question. So did you mean the pre-processing steps for the generation of the images? So that would be multi-looking and geocoding, if I have not forgotten anything. And if you mean as an input to the neural network, we tried out a bilateral filter and the Glacier filter. They both did not improve upon just using the images as is. So we did not use anything there, but I'm actually also working on incorporating a bilateral filter that is integrated into the neural network. And let's see how that evolves. I don't have any results there yet. Any publicly available code? Yes, definitely. Also from Voxel 51. They have a nice Medium, blog on how to use my benchmark dataset. But the baseline code is definitely also available. And I hope that the AMD HookNet is also available by now. And the NN unit one is also available. That paper has a preprint. It's still in revision, in review. So, but you can access the preprint, and there should also already be a GitHub link. Quick question. How long did this entire project take? How many total people on the team? Looks like 5 in the published paper. Okay. For the first version with the baselines, that was just me. It took me about a year to gather the benchmark data set and to get into the PhD life. Yeah, so that was that for the baselines. Then the one for the conditional random field, that was actually done by a bachelor student of mine, which is great. That took him, I think, half a year. And then for the other models, a colleague of mine also helped. So there we were 2 PhD candidates. And for all of the publications, I have my supervisor, Vincent Christine, and my collaboration partners, Dr. Thorsten Seehaus and Professor Brown from the geography department, and also my professor, Andreas Meyer. So yeah, that were all. And yeah, I've been at my PhD for 3 years now, so you can split that up and subtract some time for yeah, other duties that I had. Okay, are there ways that the model could benefit by including visual images in cases you have them? Yes, I am pretty sure it will help, but we aim for a model that just uses radar imagery due to the advantages that I told you of. Yeah, polar night and so on. Can this computer vision model incorporate into a model that looks at suburban and urban development? So you can definitely use my model and train it on something else. I think it's worth a try if you want. Okay, isn't the depth height of the glacier can also be an important feature to calculate its melting rate? So I myself don't calculate the melting rate directly. I just give the calving front position to the geographers, and they then calculate the melting rate. And yes, depth and height of the glacier is also important. And actually, we have a new project that is working on that with a new PhD candidate as well, where we look into the glacier with ground-penetrating radar, but that's not feasible from satellites. For that, they have to fly helicopters over the ice, which yeah, can be difficult. And then you can one time an estimate how deep the glacier is, or how high.